Okay, hello everyone. On behalf of my colleagues, welcome to this month's talk uh, from the Johns Hopkins Institute for Assured Autonomy seminar series, co-sponsored by the Computer Science Department of the Whiting School of Engineering. Each month we'll have a talk on research topics at the intersection of assurance and autonomy. The seminar will be recorded. Today's speakers are Dr. Michael Kearns and Dr. Aaron Roth. Dr. Michael Kearns is a professor in the Computer and Information Science Department at the University of Pennsylvania, where he holds the National Center Chair and has joint appointments in the Wharton School. He is founder of Penn's Networked and Social and Systems Engineering program and director of Penn's Warren Center for Network and Data Sciences. His research interests include topics in machine learning, algorithmic game theory, social networks, and computational finance. Dr. Kearns is a fellow of the American Academy of Arts and Sciences, the Association for Computing Machinery, and the Association for the Advancement of Artificial Intelligence. Dr. Aaron Roth is a professor in the Computer and Information Science Department at the University of Pennsylvania, affiliated with the Warren Center for Network and Data Science, and co-director of the Networked and Social Systems Engineering program. Dr. Roth is the recipient of a Presidential Early Career Award for Scientists and Engineers awarded by President Obama in 2016, an Alfred P. Sloan Research Fellowship, an NSF Career Award, and research awards from Yahoo, Amazon, and Google. His research focused on the algorithmic foundations of data privacy, algorithmic fairness, game theory and mechanism design, learning theory, and the intersections of these topics. Together with Cynthia Dwork, he is the author of the book, The Algorithmic Foundations of Differential Privacy. Our speakers are co-authors of the recent general audience book entitled The Ethical Algorithm, The Science and Social Aware Algorithm Design. They are also Amazon scholars at Amazon AWS. Michael and Aaron's talk is based on their book and the research challenges posed by algorithmic processes operating inside sociotechnical systems. Welcome both, and over to you.
Okay, thanks Ken, and good morning everyone. Thanks for joining us. Let me go ahead and share my screen. Hopefully everybody can see that. Yeah, so Aaron and I wrote this book a while ago, and it came out late last year. And as Ken said, it's intended to be a general audience, layperson treatment of what we're calling ethical algorithm or socially aware algorithm design. And so we're going to kind of do a tag team presentation here, going back and forth a couple of times, and just try to convey to you sort of what the spirit of the book is and what some of the topics in it are. So in many ways, our book is a complement to, or maybe even almost a reaction to, the large literature that has come out in recent years in both the form of books and also many, many mainstream media articles on the problems of algorithmic decision-making, and very often, more specifically, the problems of algorithmic decision-making when it is powered by machine learning. So some of you may have read some of these books like Weapons of Math Destruction or Algorithms of Oppression or Data and Goliath. And I think Aaron and I, we like these books and feel like they do a very good job of making real some serious problems that we have with algorithmic decision-making in consequential domains where, you know, algorithms, or more specifically models that are the result of machine learning, are making consequential decisions about individual citizens, such as criminal sentencing decisions, college admissions, consumer lending, you name it. Where we were disappointed in these books, and where our book in some ways is a bit of a reaction to such books, is when they get around to talking about not the problems themselves, but potential solutions to the problems. And so each of these books, usually towards the end, has a solution section. And in our view, we might perhaps only slightly unfairly characterize the solution section as saying, well, we need better laws, we need better regulations, we need watchdog groups, we really have to keep an eye on all these problems. And we agree with that, but as kind of card-carrying researchers in computer science generally, and specifically in machine learning, we were also of the mind, if there are things that we don't like about the way our algorithms are behaving, we could think about fixing the algorithms in the first place so that they don't exhibit these problems, or at least don't exhibit them as much, rather than, for instance, waiting for harms to be inflicted and then trying to litigate it afterwards or regulate it afterwards. And if this was all we had to say on the topic, there wouldn't be a book. But in many ways, what our book is about is an exposition, if you like, of the very, very vibrant and very, very active literature within machine learning and related communities about how we might change the way machine learning works, how we might change the way we train our models in a way that explicitly enforces social norms that we're interested in. An early reviewer of our book, when it was still in draft form, made an interesting comment that we picked up on, which is, the reviewer said, well, I like the content of the book, but the title strikes me as perhaps a bit of a conundrum or even an oxymoron. And they went on to say, like, what would you mean by an ethical algorithm? I mean, you wouldn't talk about an ethical hammer, right? So what they meant by this is that a hammer, of course, is a human artifact. It is a tool designed by people for particular purposes. And while I might misuse a hammer, I might hit you on the hand with it, nobody would ascribe sort of that ethical failing to the hammer itself. They would ascribe it to me. And we mused on this for a little bit and decided that we respectfully disagreed. And we decided that, in our view, algorithms really are different for a number of reasons. First of all, unlike a hammer, algorithms these days have a flexibility and generality of purpose that is much closer to the human mind than it is to something as specific as a hammer. Furthermore, when we say algorithm, we often mean predictive model that is the result of a machine learning training process. And it can be very difficult to predict outcomes in the machine learning workflow, and it can be very difficult to ascribe responsibility for ethical failures in that pipeline. So this is a bit of a cartoon of what a typical ML pipeline looks like. You start off with some possibly very rich, high-dimensional data set that might have been gathered from many, many different sources whose provenance is uncertain to you. But you go ahead and use that data set to define some kind of objective or error landscape for a training process, usually exclusively concerned with predictive accuracy. This results in some model that is the result of the training process that allegedly optimizes your objective function. And these days, that model might be extremely complicated itself in the form of a convolutional deep neural network. And the point is that, this process can result in harms, and even worse, you may not even realize, if I hit you on the hand with a hammer, you know it and you know who to blame for it. Algorithms can cause real harms to individual people without those individuals really being aware of the fact that the harm has been inflicted by them at all, or that it was inflicted by an algorithm. So what our book in a nutshell is about is the scientific agenda of embedding social values in algorithms. And what we mean by that is not something abstract. We mean it in the literal sense. We mean literally encoding things like privacy and fairness constraints into the Python code of our algorithms, whether they be designed by hand or whether they be a training process or algorithm for machine learning. One of the most interesting and challenging things about this scientific agenda is that if you are literally going to explain to a computer program what fairness constraints you want it to enforce, you need to be incredibly precise about definitions. You need to be precise about what you mean by fairness in a way that the many, many generations of scholars before us have never, ever had to do before. because if you have an algorithm, it's going to do something no matter what input you give it. And so you need to think about a definition of fairness that basically is precise enough that you are saying what you mean in every possible situation. And this is very different, for instance, than what laws and regulations seek to articulate about fairness. And so what we want to do with our time today is just take you through a couple of case studies, mainly on privacy first and then on fairness. And then we'll talk about other very, very current topics like explainability and interpretability a little bit towards the end. And kind of take you down the path that recent science has gone in how you would give precise definitions about these often diffuse concepts, and what the consequences of implementing those concepts algorithmically is. And there will be consequences. In general, if you ask for privacy or fairness as an additional condition that you would like your algorithm to obey, it may come, for instance, at the cost of some predictive accuracy. And so we're going to start off with a bit of a case study in fairness, for which I will turn things over to Aaron.
Thanks. And this is the part of the presentation where if we were in person, Michael would hand me the clicker, but instead I will awkwardly say slide whenever I want to go to the next slide, and we'll edit that out in post-production. So let me walk through sort of a brief history of how people have thought about privacy definitions, because I think it's informative in foreshadowing how people are currently thinking about fairness. And if you go back to sort of the early days of privacy research, and this is the early 90s, people thought about privacy in terms of anonymization. And by the way, this is actually still how privacy is sometimes encoded in regulation, in particular in HIPAA, despite the problems that we're about to talk through now. So it used to be that if you wanted to release a data set in some private way, you would think about anonymizing it, which meant removing names or maybe other unique identifiers like social security numbers. So to make this specific, in the mid-90s, the Massachusetts General Health Commission decided to release an anonymized data set of the hospitalization records of all state employees in Massachusetts. And so just to be clear, like, we're not talking about like a data breach or anything like that. This was an intentional release of information to aid in medical research, because after all, you know, it's hard to do medical research when data is unavailable, as it often is for privacy reasons. And so they released this data set, and they were very careful to remove names and social security numbers and anything else that could uniquely identify people. But the data set did include all sorts of demographic information like age and gender and zip code, so that you could correlate various outcomes with, you know, with location and age and gender. And although none of these demographic characteristics on their own, like age, is anything close to uniquely identifying, what a PhD student at MIT at the time, now a professor at Harvard, named LaTanya Sweeney, realized was that in combination, these simple demographic attributes actually were uniquely identifying. So for the majority of people in this data set, if I took the combination of their age, gender, and zip code, they were the only person in this data set with that combination. And once you have these unique triples, you can cross-reference this data set with other publicly available information and reattach people's names. And that's exactly what Dr. Sweeney did. She cross-referenced this data set with the voter registration polls in Cambridge, Massachusetts, and she found the medical records of Bill Weld, who was the governor of Massachusetts at the time, and to make a point, she sent these records to his desk. And this was sort of the first time people sort of really became aware that privacy was a hard problem, that sort of naive solutions like anonymization, removing names, don't work. But it took a long time before people thought carefully about what privacy really should be. And in the interim, people, you know, researchers would proposed solutions that didn't really attempt to enunciate what privacy was, but instead just proposed sort of syntactic band-aids to the most recent attack. And for a long time, privacy research was sort of like a cat and mouse game. Researchers would propose band-aids that would patch up the most recently published attack, and then more clever attackers would come around. And without going through all of that history, let me just tell you briefly about the first of these band-aids and why it goes wrong. And it's called k-anonymity. So if you think about Latanya Sweeney's attack, the problem was that age and gender and zip code in combination could uniquely identify people. And so the idea behind k-anonymity was to say, okay, well, maybe I shouldn't report age exactly. Maybe I should report it in, buckets of 10 years. Maybe I should redact the last few digits of the zip code. And maybe I can do this in such a way so that, no matter what demographic information I might know about a person, I make sure that I've coarsened the information in my data release in such a way so that no combination of demographic attributes matches a single record. We'll say that a table is too anonymous if any combination of records matches, any combination of features matches at most 2 records, or 3 anonymous if any combination of features matches at least 3 records. So for example, if you look at the top table here, this is a 2 anonymous record. So suppose the hospital at the University of Pennsylvania has released this 2 anonymous record of their patients, and I happen to know that my neighbor, has been a patient there, and I know quite a bit about my neighbor. I know she's, a 56-year-old woman. I know her zip code because she's my next door neighbor. When I try to figure out which is her record and learn her diagnosis, when I look at the top table, 2 anonymity succeeds in its own terms in that I cannot identify a single record. What I know about her matches 2 records. And so it has foiled this sort of most naive attempt at re-identifying her record. Now, right away, you might realize that maybe k-anonymity doesn't capture everything we meant by privacy, because although I haven't uniquely identified her record, I've narrowed it down to 2, and I've learned that she either has HIV or colitis, which already is something she might not have wanted me to know. But the problem is worse than that. The problem is that the guarantees of k-anonymity sort of entirely fall apart, even on their own terms, in the presence of additional information. And just to see an example of why that is, imagine that my neighbor's also been a patient at another nearby hospital, Pennsylvania hospital. And suppose they have released a 3 anonymous table of their patients down at the bottom. Well, again, in isolation, this table succeeds on its own terms. What I know about my neighbor matches 3 records. But I can cross-reference these records with the first table. And now, again, I've uniquely identified her record and I've learned her diagnosis exactly. And the problem really is that k-anonymity didn't define what it was trying to achieve. It just sort of imposed some syntactic constraints. And this idea of trying to hide the presence of individuals just by redacting things is sort of fundamentally broken because of the prevalence of outside information that we can cross-reference things with. Yeah, and this has led Cynthia Dork to give sort of the memorable quote that anonymized data isn't. Either you haven't really anonymized it, or you've sort of scrubbed so much information from the data that it's not even useful data anymore. And so let's think about how we can do better. Slide. So let's now go in the other direction, try to enunciate some ambitious desideratum for what privacy should mean, and then think about whether we can achieve it. And our first attempt at this is going to be a little bit too strong. So, okay, what does privacy mean? Well, ambitiously, maybe we could say that a data analysis is privacy preserving if I can promise that nobody can learn anything about me or about any other participant in the data analysis after the analysis was performed compared to what they already knew about me before the analysis was performed. I mean, that would be like a good definition of privacy if we could achieve it, if if conducting some data analysis literally revealed nothing about me to anyone. And that would be a good definition. Well, that definition's a little bit too strong, and let's think about why. So imagine that you were one of the 2/3 of British physicians who participated in what has now come to be known the British Doctors Survey. This was sort of a study conducted in the early 1950s that provided the first large-scale evidence that there were strong correlations between smoking and lung cancer. And 2/3 of British physicians participated in this. They gave access to Dahl and Hill to their medical histories and their smoking habits. Now, before this study was published, if you were a doctor in Britain who smoked, the fact that you were a smoker would not have been a secret. It's not something you would have hid. There was no stigma around smoking at the time because, after all, we didn't know that anything was wrong with smoking. But after the study is published, if I read it, I know something new about you, right? I already knew that you were a smoker, and now I've learned this fact about the world, that smoking and lung cancer are correlated. And so now I have a updated, higher belief that you might develop lung cancer. But I know something new about you. And by the way, this is something that could cause you real harm. For example, if you were in the United States, this might actually cause your health insurance rates to rise. This is causing you sort of quantifiable dollar harm. And so, the question is, should we take the position that what has happened to you is a violation of your privacy? After all, I've learned something new about you. And I want to claim that we should not, for two reasons. The first is purely practical. If we call this a violation of privacy, then it is not possible to do any kind of data analysis at all while respecting privacy, because for any correlation in the world at all that I might learn between a publicly observable attribute about someone and something they don't want me to know, discovering that correlation would, in this definition, be called a violation of privacy. And if we can't learn about any correlations at all in the world, there's nothing useful we can do with data analysis. But the other reason is sort of more fundamental, which is that this story plays out exactly the same way, even if you were one of the doctors who didn't participate in the study, or even if you were born many years after the study, because the fact that was sort of revealed in this journal article that supposedly violated your privacy was not a secret that was yours to keep. Right? I didn't learn something about you. I learned a fact about the world, that smoking and lung cancer were correlated. And I could have learned that fact with or without your data, because it's a true sort of correlation that holds broadly in the world. I could have learned that fact from any sufficiently large sample of the population. And it seems funny to call such things violations of your privacy if I could have learned them without access to your data at all. And that suggests what was sort of a definitional breakthrough in 2006 called differential privacy. Slide. So differential privacy asks for something similar and almost as strong, but something that is actually sort of a little more sensible and a little more achievable. So just as in our example with the British Doctors study, differential privacy is defined by considering the real world and some idealized hypothetical world. Now, in our overambitious definition that we talked about with the British Doctors study, the sort of idealized hypothetical world was the world in which the study was not conducted at all. In differential privacy, the idealized hypothetical world is a little bit different. In the idealized hypothetical world, the study is still conducted, but it's conducted without your data. That is, these two worlds, the real world and the idealized world, are the same in every respect. The study is conducted in both cases, except that in the idealized world, your data is not used. Everyone else's data still is. And differential privacy asks, in some particular quantifiable sense, that no outside observer should be able to learn much more about you in the real world compared to in this idealized world. And by making this distinction in which the idealized world is the same, the study is still conducted except without your data, it manages to sort of tease apart this distinction between secrets that are yours to keep, things that couldn't be known except through access to your data, and facts about the world that sort of are the aim of science to discover and that aren't your secrets to keep. Things like the correlation between smoking and lung cancer. Slide. Now, if you sit and meditate on this definition, I hope, like many others, you will agree that it is a sensible and strong formalization of one kind of privacy. But you might have the concern that although it is a strong notion of privacy, perhaps it's still too strong. Maybe there's nothing useful we can do while satisfying such a rigorous notion of privacy. And it's not obvious, but fortunately, sort of what we've learned over 15 years of research is that that's not the case. In fact, almost any statistical task, things like machine learning or regression or other kinds of statistical analyses, things whose accuracy we define with respect to the underlying distribution and not with respect to particular data points, can be done subject to differential privacy, although not without some cost. There's typically some cost when we ask for more privacy in some quantifiable way. In order to achieve it, we need also more data or less accuracy. And just to give you maybe a little taste of how you might do a very simple statistical analysis subject to differential privacy, imagine I wanted to conduct a survey for the participants in this webinar. And I wanted to ask a question that maybe had some social stigma. So I want to ask, have you violated social distancing guidelines in the last week? And so, I could say, okay, everyone just, enter into the chat whether you've violated social distancing guidelines, but you might not want to do that because the answer is embarrassing. And so what I could do instead is I could say, okay, flip a coin and don't tell me the outcome, but if it's heads, tell me the true answer. And if it's tails, tell me a random answer. Flip the coin again and just, tell me yes if it's heads and no if it's tails. And the beautiful thing about this is that any particular individual has a strong form of plausible deniability. That is, if you type yes into the chat and later I waggle my finger at you disapprovingly and say, why did you violate social distancing guidelines? You can say, well, I didn't. I was just following the protocol and I flipped the coins and it told me to answer no. But nevertheless, in aggregate, I can get quite an accurate estimate of the thing that I wanted to know in the end, which was what fraction of people in the webinar violated social distancing guidelines. And the reason is because I know exactly the probability distribution that people were using to provide their answers. And so, for example, for every fraction of the population P that might have violated social distancing guidelines, I know the expected fraction of the population that's supposed to answer yes. And similarly, given that I can see the fraction of the population that actually answered yes, I can work backwards and get an unbiased estimate for the fraction of the population that actually violated social distancing guidelines. And the answer will be noisy, but by the law of large numbers, essentially, the bigger the population is, the more I can sort of cancel out this noise, the more accurate an answer I can get. Yeah, and this actually turns out to be maybe the simplest example of a differentially private algorithm. And this is a differentially private algorithm that has some particular privacy parameter, but by adjusting the probability that you answer truthfully, I can quantitatively dial up and down privacy in the form of stronger or weaker claims to plausible deniability for the participants at the cost of noisier or less noisy estimates. Slide. And so for, maybe the first 10 years of its life, differential privacy was primarily a topic studied in the theoretical computer science community. People like me would write, mathematical papers for maybe, a few dozen other people like me. But what we've seen in the last 5 years is that differential privacy has become a real and widely deployed technology. So if you have an iPhone, it's reporting statistics back to the mothership as we speak in a differentially private way. It's also done in Chrome. In the early days of the pandemic, Google actually provided a useful tool that provided mobility reports in all sorts of different locations using differential privacy. So you and I all carry little surveillance devices around in our pocket. So Google has access to very fine-grained location data for 1 billion people. And during the pandemic, we wanted to know how how effective stay-at-home orders were. When was a good time to go to the grocery store, things like this. And Google could have released very sort of precise information about the location of all of its users, but that would have been an egregious privacy violation. But it didn't need to. It could use differential privacy because the only thing we really needed to know were sort of statistics, roughly how many people are in each location at each period of time. And so these mobility reports were released subject to differential privacy. Slide. The other big use case we've seen this year is the 2020 census. So the 2020 census is going to release all of its statistical products for the first time, subject to the protections of differential privacy. And this actually gets to sort of the tricky social questions that are going to come up again with fairness and arise also with privacy, which is that there are real trade-offs we need to grapple with. Privacy doesn't come for free. We can ask for more privacy, but at the cost of less accuracy and vice versa. And it's not clear how we should manage these. So privacy is important. And in fact, it's mandated by law that the census preserve the privacy of American citizens. On the other hand, the data it releases is also used for sort of important downstream tasks, including allocating federal funds. And the more privacy you ask for in the sort of units of differential privacy, the less accuracy you are going to get, which manifests itself in real ways, as people are already worrying about, as in this headline. And how exactly to make that trade-off is something that the science can elucidate. It can elucidate what the trade-off is, but it's not something that the science can decide. And I'll turn it over to Michael again.
Okay, thanks, Aaron. So in a similar vein, I'm going to talk a little bit about fairness and try to give you a taste of what the state of the art in thinking on this topic is in machine learning and more generally. Compared to privacy, and particularly to differential privacy, which, as Aaron suggested, has really become a definition of privacy that large numbers of people who think carefully about privacy have rallied around and kind of converged on as the right notion of privacy, even though it of course can't promise everything that somebody might mean by that word. We know that fairness is going to be messier. So it's not only is it much more of a work in process in the sense that the research is more nascent, it's less mature, it's maybe 10 years behind where differential privacy is now. We already know that there won't be something like the differential privacy of algorithmic fairness, a single definition that encompasses much of what we want. So not only is there not widespread agreement on definitions, we actually know that there are entirely reasonable definitions of fairness that are in outright conflict with each other. So even just in the past couple of years or so, there have been papers that basically take the following form. The authors start off and say, well, look, here are three different definitions of fairness, or here are three different properties that you would want any definition of fairness to meet, right? And you look at these three properties and you nod your head and say, yes, of course I would want these properties. These are very weak properties. I would want these and probably other ones as well. And then the punchline of the paper is a theorem that says, well, guess what? Except in trivial, unrealistic, uninteresting cases, you cannot here's a proof that you cannot simultaneously achieve these three properties. So we really need to entertain multiple definitions, and that means that picking the right definition for any particular use case will be important. And it's not only that there can be outright mathematical conflict between different definitions of fairness. There can be the same kind of trade-off between the amount of fairness you ask for and the accuracy of your predictions, as there was between privacy and accuracy and differential privacy. And to put a fine point on it, you really might find yourself confronted with a data set in which asking for more of some kind of fairness by race forces you to accept less of that same kind of fairness by gender. And so we're only just beginning to understand these trade-offs between different types of fairness and between fairness and accuracy, but it's off to a good start. But it definitely means that there will need to be serious dialogue between, scientists and engineers who think about these topics and the stakeholders who are picking a particular definition of fairness and how much of it they want to demand in a particular use case. But before we get too far ahead of ourselves, probably many of you have seen the steady drumbeat of articles that you can find in the mainstream media these days about either, very carefully done scientific studies or anecdotal reports of discriminatory behavior by algorithmic decision-making and models. So on the lower right here, I have, a headline from about a year ago, shortly after the Apple credit card, which was underwritten by Goldman Sachs, first came out. And a number of luminaries in the tech community basically, tweeted things like, well, isn't this strange? My wife and I file our taxes jointly. She has the higher income and the higher credit rating, yet my Apple card has 10 times the credit limit as hers does, okay? And so, even though a few tweets by tech luminaries does not constitute scientific proof of discriminatory behavior, in other instances, we do have such proof. And so how does this happen? Why might machine learning result in predictive models that are demonstrably unfair by race or by gender or by other attributes that we might want to protect? Is it because, machine learning scientists and engineers are incompetent or are racist and are kind of programming in little backdoors that are bypassing the normal principles of machine learning? The answer is no. And the answer is in some ways worse. The problem actually lies with the standard scientific principles of machine learning itself, as I'm going to try to demonstrate in the next few slides. But the good news is that once we see what the problem with the vanilla principles of machine learning are, the fix is at least conceptually relatively straightforward, as we'll see. Okay, so kind of like the databases that Aaron used to, describe anonymization and privacy and how it was broken, I want to just use a toy example to describe how machine learning in its normal form can result in discriminatory behavior, okay? So in this little vignette that I'm going to take us through, imagine that the admissions office here at Penn asks me and Aaron to help them develop a predictive model for college admissions, okay? And so to keep things simple, we'll have a little two-dimensional example. So imagine that we're going to try to predict whether individuals would succeed at Penn if they were admitted from just two things: their high school grade point average, which will be represented on the x-axis, and their SAT score, which will be represented on the y-axis. So each one of these green points has an x value giving the GPA of the applicant and a y value indicating their SAT score. And we're going to try to develop this model from historical data. And in particular, we're going to develop the model from historical data, not just of applicants, but students who were not only even accepted, but actually matriculated. They actually came and attended Penn. And since this historical pool of applicants who actually attended Penn, since they attended Penn, we know whether they succeeded here or not. And for the definition of success, pick any quantitative, objectively measurable definition of success. Let's say graduated within 5 years of arriving at Penn with at least a 3.0 GPA in college, okay? And so that's what the pluses and minuses indicate here. The pluses indicate matriculants to Penn that met that criteria for success, and the minuses indicate students that came that did not meet that criteria for success. And this cloud of green points looks more or less like you might guess. It tends to be the case that the pluses are higher and to the right, higher GPA in high school and higher SAT score. And the minuses tend to be lower and to the left. And even if you don't know anything about machine learning, if I ask you to eyeball this cloud of points and pick a good predictive model that we could then apply on a forward-going basis to new applicants to Penn, you might very well pick this blue decision boundary, this blue linear classifier, as we would call it in machine learning, which basically predicts positive for anything that falls above this blue line and negative for anything that falls below. Okay, and notice that it's not perfect. It makes some mistakes. So here are some false acceptances. These are students that this model would have accepted that in fact did not succeed historically. And perhaps even worse, it makes a couple of false negatives. These are students that would have succeeded or did succeed that this model would have rejected, okay? But it's pretty good. It's a pretty good model, right? Now, suppose I told you that this, though, was not the entire cloud of data points, that there was another subpopulation of the data points, these orange points, okay? And there's a few things I want you to notice about the orange points. First of all, the oranges are a minority in the literal sense that there are far fewer of the orange points than there are green points. Secondly, there seems to be something systematically different about the cloud of orange points. In particular, their SAT scores seem systematically lower, right? The orange cloud seems shifted down along the y-axis compared to the green cloud. And if I had to make up a story about why that might be the case, I might offer the narrative that the green population is from a wealthy demographic in general. And being from a wealthy demographic, they have the time and money to pay for SAT preparation courses and multiple retakes of the exam, all of which take time and money. And that the orange population, being from a less wealthy demographic, they can't afford that. So they do a bit of self-study, they take the exam once, they take the SAT once, and they take whatever score that they get. But despite the fact that their SAT scores seem systematically lower, it is not the case that the orange population is less successful in college. In particular, if you counted the green points very carefully, you would have discovered that slightly less than half of the green points were successful at Penn. And in the orange population, it's exactly 50-50, okay? So the problem arises, and if I asked you to pick a predictive model just for the orange population, you very well might pick this purple linear classifier, which does a perfect job of separating pluses from minuses. The problem arises when I now step back and look at the combined cloud of orange and green points, and I ask myself, what is the predictive model that makes the fewest mistakes on the combined data points, okay? And by the way, this is what the standard principle of machine learning would do. Whether you're building a linear classifier or a deep convolutional neural network, in general, your goal is to find the model which has the lowest error on the historical or training data. And in the case of this particular data set, that will unfortunately be exactly the same predictive model that you would have chosen on the green population below. And it's pretty clear why this is the case. If I try to shift down this blue classifier, this blue line, far enough to accept these 5+ orange points, I will pick up so many green minuses along the way that my overall error will increase significantly, okay? So this blue classifier really is the model that maximizes the accuracy on the historical data, but it also, it is also taking us to the point where now we can quantify the sense in which this model is unfair. If I think of the type of mistake that is the greater harm in college admissions is false rejection, namely not admitting students who would have succeeded here, the false rejection rate of this blue model on the green population is close to 0%, and the false rejection rate on the orange population is 100%. So if I define fairness to be equality of the false rejection rates between the two populations, this model, which happens to maximize the overall accuracy, is also about as unfair as we can get, okay? Now, you might be thinking, well, this is silly. Why don't I build a two-part model? You know, supposing I know that, suppose I know whether applicants are from the green or the orange subpopulations. I could just have a two-part model that says, well, look, if you're green, I'm going to apply the blue threshold. And if you're from the orange population, I'm going to apply the purple one. And now, not only will I eradicate the unfairness of the blue model in isolation, I will have improved my overall error as well. So it's like a win-win situation. Unfortunately, to the extent that laws and regulations are precise on what fairness means, if, as I've kind of suggested, green and orange are stand-ins for race, in consumer lending, for instance, in the United States, this kind of model, this kind of two-part model would be illegal because it looks at race as an input, right? The model first looks at the race, orange or green, and then decides which model to apply, which is itself a model that involves race, okay? And so kind of like k-anonymity for privacy, this type of definition of fairness, where you try to get at fairness by forbidding the use, for instance, of race or gender as an input to an algorithm or a model, is fundamentally broken. And this example shows that even though I'm sure that when such consumer lending laws were developed in the United States, they were well-intentioned, you know, that somehow there was this magical thinking that by forbidding the model from looking at race, you must get fairness by race, right? So this example shows that not only is that not true, but in this example, you're actually guaranteeing harm to the very group that you thought you were protecting with that kind of fairness definition. And so what's the right definition of fairness? What should we do in a situation like this? Well, what we should do is change the objective that we train our model for. Rather than simply saying, find the model which minimizes the overall predictive accuracy on the combined cloud of points, we could change that objective to a slightly more complicated one in which we say, find the model which minimizes the overall error, but subject to the condition that your model roughly equalize the false rejection rates by the two populations. And by roughly equalize, I'm going to introduce a knob here, right? I could basically say, find the model which minimizes the overall error, subject to the constraint that the false rejection rates on the two populations has to be identical. And so that's like the strongest type of fairness constraint of this variety that I could ask for. Or I could say, okay, you're allowed for the false rejection rates to differ by 1% or 5% or 10%. And obviously, if I let that knob go up to 100% disparity in the false rejection rates, then I'm kind of back with normal machine learning where I'm not enforcing any fairness constraint at all. And in general, we should expect that the stronger the fairness constraint I ask for, the tighter I want to make the discrepancy between the two false rejection rates, the more that might cost me in overall accuracy. And in fact, you can literally plot out what these trade-offs between accuracy and unfairness look like on real data sets. So what I'm showing you here, for instance, on the left, is the results of an experiment on a real data set in which fairness is a concern. And each red dot here is a different model. So think of each red dot as being a different linear classifier in the cloud of points on the last slide. And for each one of these red dots, its X value is the overall error on the entire population of that model. And on the Y-axis is the difference in the false rejection rates or some similar notion of fairness between two populations or perhaps multiple populations if we're looking, for instance, at multiple different racial groups, okay? And of course, you know, since lower error and lower unfairness are always good things, we wish we were down here at the origin at 0, 0. You can see that we don't achieve that in any of these plots because in general, machine learning on real data sets is hard. And so even ignoring fairness entirely, the smallest error we get is still non-zero. But you can see that these models trace out a menu of options that we have, right? We can ask for the lowest error, and then we'll get the highest unfairness. We can ask for zero unfairness, but then we'll suffer much higher error. And in between, we get something in between. And we argue in the book that kind of figures like this are a promising interface between machine learning scientists and engineers and policymakers and stakeholders in particular application domains. Because if, for instance, this is the trade-off between accuracy and unfairness in, let's say, a criminal sentencing application or in college admissions, Aaron and I can plot these curves out, but we shouldn't be the ones that say, okay, well, now that I see the curve, this is the right model that we should use, right? Somebody who is an expert in college admissions or criminal sentencing and the downstream consequences of, accuracy versus fairness should be the one making those kinds of decisions. So we can show them this menu of options, but people who are really kind of embedded in the particular use case need to be the ones who understand what this diagram is telling them and make the decision about what trade-off they're willing to tolerate. Okay, with that, I'm going to turn it over to Aaron to wrap things up for us.
All right, so I know we want to leave a couple of minutes for questions, so I'll be brief. But what we've heard about so far are essentially the first two chapters of the book, in which we focus on privacy and fairness, but for algorithms in isolation. But of course, algorithms are rarely in isolation. Typically, when we deploy algorithms, they are parts of sociotechnical systems, if you will, by which we mean systems that might be mediated by algorithmic decision-making, but involve in large part human decision-making as well. So for example, in criminal justice applications, there really are algorithms that try to predict whether people, if released on bail or parole, will go on to commit new crimes. But the algorithms are not, in fact, making the criminal sentencing decisions that human judges are. When we think about algorithms deployed to mediate, for example, news feeds on Facebook and Twitter, the algorithms are mediating the interactions between huge numbers of people whose decisions about what to click on and what to view really matter. And in cases like this, it's not enough to think about algorithms in isolation to reason about social values like fairness or privacy or other things. We need to understand how tweaks to the algorithms will change the system at large. And in the third chapter, we sort of argue that game theory, and in particular algorithmic variants of game theory, provide the right rules to think about these things. We also think about the reproducibility crisis, the fact that in some areas of science like social psychology or food science, it seems in recent years that if you flip to a random page in a journal, the result that you find reported is more likely than not to be reproducible. And that seems a little bit far removed from the other topics of the book, but it turns out the other topics of the book have something to say about this. And there was a question in the Q&A about whether differential privacy or fairness techniques have value outside of social impact. And the answer is yes. So it turns out that techniques for differential privacy can allow you to adaptively reuse data to do the kind of thing that normally leads to p-hacking and these non-reproducible results in a way that allows you to endow your conclusions with guarantees of statistical validity. And then finally, in the last chapter, we survey a bunch of important areas like interpretability and accountability, in which people are spilling lots of ink, but about which there is so far less to say of sort of the sort that we want to say, in that people have yet to pin down definitions. So as we saw in the privacy section and sort of the fairness section, progress comes when we figure out exactly what we mean by these words. And the interpretability literature is, at this point, I think, like the privacy literature before differential privacy, in that people are proposing syntactic notions that they are calling interpretability. Then other people are coming around with clever attack papers showing that you know, the existing methods perhaps are less interpretable than you might think. And progress will come when we end this cat and mouse game and figure out what the right definitions are, but we're not there yet. And with that, let me wrap up and we can take a couple questions.
I want to thank you, Michael and Aaron, very much for your excellent talk and describing both the principles in the book as well as the application to some real-world examples. We have some questions left, and you've been answering a few of them real time, which is outstanding. Before we start with that, I just wanted to ask you, there was a point you made, Michael, in a recent NeurIPS seminar, keynote talk by Charles Isbell about the need to bring more people with backgrounds in these areas of law, of mortgage lending, of real estate into making these models. Could you expand on that a little bit? It can't be all left up to computer scientists, or they may not have computer scientists available to them.
Yeah, so what I said there was, the topic was on the importance of basically having a diverse set of people, even in the kind of design phase of machine learning or an algorithm making decisions, or a product involving AI or machine learning. And and as I mentioned in that talk, right, my thinking on this has changed recently. And so I think this is especially true in settings when you're using AI or machine learning to build a product or service whose eventual uses you may not be in control of or may not anticipate. So in the example I gave of, college admissions, in that example, we're making a very, very precise decision. We're building a predictive model from historical data of collegiate success, and we're building a model to make accurate decisions overall, but we're also worried about a fairness notion, in this case, the harm being false rejections, okay? If you think about something like face recognition, right, where we're taking a bunch of images and we're training some, deep neural network to do a good job at face recognition, and then we're going to offer that as a product or a service, it can be, unlike the college admissions example, it can be very hard to put your finger on exactly what might constitute harms inflicted by that technology, because you may not know how parties will use that technology. So in particular, if, I train my face recognition system on a bunch of images, scraped from Instagram and the internet, and I build a really good model, and I might even enforce different fairness constraints. I might make sure that, my model seems to be performing equally well on different racial groups, on different gender groups within my training data, okay? And then I find that, some downstream party has decided to use my product or service on grainy surveillance video frames, in low lighting conditions where people's faces are, at an angle to the camera rather than looking straight on and smiling. So first of all, that's a very different environment from which I trained. And there might be fairness considerations, for example, in that use case that I simply wasn't thinking about when I was kind of testing for fairness in the lab on the training data that I was building the model from. And so I think in those kinds of settings, it's very, criminal justice applications, I think are also ones where it's very important to have people who, first of all, can think about ways this might be used that, a narrow group of people might not do as good a job at, and also can think about what the harms of different use cases are that a more narrow group of people might not think about.
Thank you. So another question on the board is how can you determine the most ideal and widely accepted social values to embed in algorithms?
Yeah, so that's a good question. It's a hard question, and also I think something that sort of is not in the purview of computer science. So we're careful in the book to try to make the distinction that although computer scientists have a crucial role to play in formalizing, in mathematically precise ways, like real semantically meaningful mathematical constraints that sort of reflect these social norms. It's not up to us to figure out, or it shouldn't be up to us to figure out which of these social norms we actually want to enforce. And how to do this in practice is a tricky question, because of course there are sort of language barriers between different populations of even amongst academics who think about these things, right? So it's hard just because of sort of different beginning assumptions and different terminology to talk to philosophers or economists or sociologists or legal scholars. Some of that dialogue is starting to happen. There's a great interdisciplinary conference on these issues called FACT, which actually brings in people from all of these fields. And so I think a important precondition for a real dialogue to happen is that there's a community of people who sort of become bilingual across these fields. And we're at the beginning stages of building such a community.
Thank you, Michael and Aaron. I'm afraid we're out of time. I will ask if there's any of the panelists that wanted to give one final question. Then I think I'll just thank you and thank the attendees. And we look forward to seeing everybody next month when we have our next seminar. Everybody stay safe and have an enjoyable holiday. Thank you.
Thanks for having us.
Thank you.